All right, let's resume. So let's look a bit live into the first part. So as some of you have noticed and reported on the chat, the initial simulation kernel that I give you at the end of the first chapter performs really, really slowly. That's expected. Right in the next chapter, we'll start seeing what are the things that go wrong and how we can improve performance using partly some of the techniques we've seen in our first Rust chapters and partly some other techniques new to this chapter. So to do that, let me share my window. So let's cover together perhaps the second chapter. So assuming you ran a CPU profiler on the initial naive code that I gave you, you would find, perhaps not in a super obvious way because the output on compiler, those tend to not always be super obvious, that the code spends large, I would say an acceptable amount of time computing which indices of the concentration tables should be targeted by the input stencil and slicing the input tables at this location. So let's step back. What do I mean by that? By that I mean that when we compute the discrete Laplacian, what we are effectively doing is computing a weighted sum of the neighbors of each cell, each concentration cell in the simulation domain. However, we cannot always, just take the left neighbors, the right neighbors, the top neighbors, bottom neighbor, and the diagonal neighbors, because our simulation domain is finite. It has to fit into our computer's memory. And that means that we need to use some kind of trick to make sure that we do not try to index concentration cells that do not exist when we reach the end of the simulation domain. And the trick looks like this currently in the naive code. So I take the output position for each coordinate. That's just a small utility function I defined. I take the output position, subtract the size of the stencil, which for this 3x3 stencil is 1. And I do a saturating subtraction, which means that if the outcome of the subtraction would produce a negative index, instead it produces 0. Similarly, on the far side, so for the bottom right coordinate of the stencil, I make sure that I do not go out of bounds by computing some maximum with respect to the size of the concentration array. I then take these start and stop coordinates, top left and bottom right corner actually, and I turn them into rest ranges, and this allows me ultimately to create an ND array slice. From this slice, I am then able to iterate over the relevant points of the concentration and apply the stencil computation. So effectively, what I'm doing is to implement some complicated version of a sliding windows iterator with some edge cases on the borders of the concentration. And unfortunately, that code is too complex for the compiler to make sense of it. Just to step back, by the way, why am I allowed to just ignore some stencil points? Actually, what I'm doing implicitly here is I'm using what's called a zero boundary condition. I'm stating, actually, I cannot simulate an infinite simulation domain, so I will just assume that the concentration of each chemical species is 0 on the edge of the simulation domain. And if the concentration is 0, it means that the contribution of this concentration to the Laplacian will also be 0, because 0 times some weight is 0. And thus, I can just ignore those points of the concentration when computing the Laplacian. That's good. but even if it's correct, as we've seen, it's too slow. So is there a way we could perhaps use the sliding windows iterator of ND-array instead of making our own and having some irregularities? Well, yes, and no, we do need to take some precautions to get there. When we do that, the problem is the number of sliding windows that we will get is not the same as the number of output elements that we have in the U and V concentration arrays. This is best seen with some visualizations. Unfortunately, I did not make sketches for this particular chapter, but you will trust me that there are two less windows than there are concentration elements on the grid on each dimension, horizontal and vertical. And we can resolve this in two different ways. There are two classic approaches. The first approach is to complicate our data layout. In this approach, what we would do is to make our concentration tables larger by adding a strip of 0 elements on each side. And then we need to be very careful in all subsequent compute code that we will never actually touch this 0 on the size of the simulation domain so that it stays at 0. That's one first approach. The second way we can go about it is to, instead of making the data more complicated, make the update loop more complicated. And in that case, what we do is we will split our current loop into two different code paths. One which processes the center of the simulation domain with optimal efficiency, because at the center we don't have these boundary conditions to take care of. And another loop that takes care of the edges. It will be less efficient, but that's okay, because for sufficiently large simulation domains, the contribution of the edges to the computation time, total computation time, is insignificant. And there are pros and cons to each approach. The first approach makes your simulation update loop simpler at the expense of making you think about a strip of 0 in every other part of your code base, including the DAY3 output, for example. Whereas with the second approach, you do not pollute your entire code base with something that is only a concern to the update loop. However, you will have a more complicated update loop with some redundant code. So yeah, it's up to you then to see where you should spend your code complexity budget. What I will show you is what the code looks like when you do actually take care to optimize the central iterations. So in that case, what you do is you take your starting concentration, for example, you take the shape of a concentration table, and you define a central slice that goes from the second element to the element before the last element. Beware that this is an right exclusive range. And when you have such a slice, you can use it to slice the output tables to only get the center elements. You can combine iteration over these slices with iteration over 3x3 input windows from the starting concentration. And in the end, you will get a computation that works to produce one output element for U and V from one 3x3 window from U and V. And as you see, when you do that, the simulation code gets a whole lot simpler. It's much cleaner, and unsurprisingly, perhaps, it will also be significantly faster. Of course, then I ask you to, as an exercise, to produce a full simulation from that. Because right now, the way it's spelled out, I'm only computing the center element of the simulation domain correctly. I'm not updating the edge elements. And if you run this simulation, you would see that this will result in artifacts on the edges after a while. So you need to handle the edges. The question is how. Moving on. After you take care of that, you will see that you get some performance benefits. There is, however, another performance problem that you would find with more advanced profiling, like using the assembly view of perf, which is that the code is not vectorized, which, if you remember, means that we are throwing a large performance factor out of the window. The reason why that is the case is if you look into what this code is doing, effectively for each concentration value that you emit, the code computes the equivalent of one tiny dot product between one vector of weights and one vector of concentration. So weights from the stencil and concentration from the input concentration window. And the problem is, as you have perhaps understood from the last chapter, dot products of small vectors do not vectorize very well. And the compiler, unfortunately, is not clever enough to implement more clever vectorization schemes here. So we'll have to do it ourselves. What would we do? We could try to outperform the compiler and do a fast dot product, but again, 3x3, the dot product of two 9-dimensional vectors will never be super efficient on modern CPUs. CPUs are good at manipulating large chunks of data in a SIMD fashion. Here with 9 elements, we do not even have enough elements to fill one single AVX512 SIMD vector, so that's not good. The alternative would be to modify our simulation loop so that on each outer iteration, we do not just compute one pair of concentration values, one for U, one for V. We compute one full SIMD vector of concentration values. And for this whole SIMD vector, we will do the same computation that we did before, but in SIMD. I would argue that this approach is a lot superior. It will scale to larger vector sizes. It vectorizes the full computation, not just the Laplacian. And it does have one drawback, however, which is that here it works for this simulation because our code has a relatively simple logic that is amenable to SIMD computation. If each iteration of the simulation loop was more complicated, like it has some conditional branches, virtual methods, and so on, then we would not be able to easily perform the computation in a SIMD way. We would have to use some more advanced SIMD techniques like masking, which reduce performance. And ultimately, it's not clear if SIMD would be worthwhile at all. So we are in this situation where we can afford to, so let's do the vectorized computation. So here the goal is this. So initially, our computation, the regular part at least, looks like that. So we are iterating over the simulation domain. We are taking 3x3 input windows in blue, and we are producing in the output array one output element, which is dependent on all concentration values from this window. What we want to do instead is to get to the point where we are iterating over SIMD vectors of outputs. And then our window is made larger by that much so that it's still one extra element on each side. And now we want to compute this many elements by taking this SIMD vector and doing the usual stencil computation, but taking this SIMD vector, this SIMD vector, this SIMD vector, this SIMD vector, and not this element, this element, this element, this element, this element in a scalar way. It's not that easy, however. So far, our scalar code was symmetrical in how it handled the vertical and horizontal dimension. And this means that we could afford ignoring completely the fact that our iteration is two-dimensional in nature. And we could just have a 1D looking iteration. With SIMD, we cannot anymore because now we've been saying that rows are different from columns. So just to give you an example here, you can see that we have a single loop. Actually, we are flattening the two-dimensional loop. This we cannot do anymore. So instead, we will need to have a double loop, one loop that iterates over lines of output elements, which underneath has a second loop that iterates over SIMD vectors within each line of output elements. And then we will produce each SIMD vector of output element. In doing so, we will also need, as usual with SIMD, to decide how we handle the case where the number of output elements in our simulation domain is not a multiple of the SIMD vector length, which is a hardware constant. We could decide to simply say that this is not allowed. That would keep our code simple, but some users may become angry. We could decide to handle the remaining elements of each line of the simulation domain using a scalar computation, like the one we have previously written. Or we could start by slicing up a regular part of the computation that has all the right properties for SIMD. We would process it in our preferred way, and then we would finish using a more general but slower scalar implementation to handle all the edge cases. My advice is all of these options can be good in different circumstances, but when you don't know, this option is often the good default answer. So what I will do then is to show you how to do the easy part of the computation. So first, I am going to take the number of rows and columns in my simulation domain from the concentration array shape. And I'm going to decide what is the subset of the output that can be easily computed using SIMD. So first of all, I know that the elements on the left and the right cannot be easily computed because they do not have a full 3x3 window of concentration elements around them. So these I ignore. Then of those remaining elements, I do a kind of division that truncates to an integer number of SIMD vectors, and I gain back to the associated number of elements. Finally, I extract the relevant part of the output array, the matching parts of the input arrays, and then with some more complicated iteration code, I can get where I want. Once I have a proper iteration, so first, yeah, here what I did is I started iterating over rows of the regular part of the output and over triplets of 3 rows that match in the regular part of the input. I do that. Then inside of that outer loop, I go into an inner loop where I take my output row and I do a chunked iterator that extracts me a number of elements that's equal to my SIMD width. So now I will be iterating over output SIMD vectors, and then I will be able, using some a bit fancier ND array expression, to extract matching windows from the initial triplet of rows from the input array. Once I've done that, I finally get to the point where I have SIMD vector of outputs and the matching window of inputs, and then I can introduce some explicit SIMD code using std SIMD in order to do the same computation as before. The main difference here is that I need to initially load the data from the scalar slice of scalar inputs. Whenever I have a scalar constant in my code, stencil weight, diffusion rate, feed rate, I need to turn that into a SIMD vector, which is splatted, which is STD-SIMD vocabulary for taking a scalar element and producing a SIMD vector where each element of the vector is equal to the original scalar element. And given that, I get a computation that has almost the same shape as what I had before. And in the end, I need to write down my vectors to memory. That's a fair bit of work, especially when you take into account the fact that then you need to handle the sides of the simulation domain, but you can get it to work. However, we can do better. What we can do is to do more powerful SIMD computation by changing the layout of our data inside of the concentration array. So to clarify, the version of the SIMD code that I've shown earlier has two major issues in my mind that might be worth improving upon. The first one is that the SIMD update loop, as described in the previous chapter, becomes a lot more complex than the regularized Scala code that I had been producing earlier. You know, when I see that, I'm happy. I would like my code to stay that way and still be performant with SIMD and all. And right now, that's not what I have. And second, on the hardware level, this SIMD loop is not as performant as it should be because I get memory alignment issues. By that, I mean that since I'm processing output SIMD elements starting from the element at coordinate 1, 1 in the concentration table, it means that if I take x86 CPUs as an example, in my SSC builds using SSC vectorization, 1 in 4 memory accesses will fault because we will get a SIMD vector that straddles 2 cache lines, and that results in a slowdown. 1 in 2 AVX accesses will fault in a similar way, and every memory access will fault in a similar way if you use AVX 512. So the more advanced your CPU SIMD capabilities, the worse you will pay for this misalignment penalty. And what I want to show in this chapter is that we can resolve both of these issues and get a simple update loop and with no data alignment issues in exchange for paying a price in a different area. We will get data with a layout inside of memory that is a lot weirder, less obvious, harder to reason about. We will have a hard time interoperating with other code that expects standard scalar memory layouts like the ADA5 IO library. We will basically need to convert from our optimized SIMD layout to the standard scalar layout. And if we save data to ADA5 too often, that will cost performance. And finally, this is the point where I will personally give up on the idea that we can allow users to pick a simulation domain of any size they like and start enforcing some hardware-originated constraint on the problem size in order to make the code simpler on our side. Let's assume that you are okay with all of these drawbacks. What do we do? So let me show you what our 2D concentration data looks like, and I give each element in the concentration table a number. And let us assume that we are working on some weird hardware that has SIMD vectors of width 3. The first steps of the translation to the optimized SIMD layout will be to take our simulation domain and cut it into 3 equally sized vertical parts, which here I have highlighted in purple, blue, and green. So far I have done nothing, just taking the data and saying I am discriminating top block, middle block, bottom block. The magic of the optimized SIMD layout happens when we start taking this and produce a different data layout, which is composed of the first column of the top block, followed by the second column of the by the first column of the middle block, the first column of the third block, and we repeat with the second column, top, middle, bottom, and so on, which looks like this. And at this point, you may think I have gone crazy, and I will not blame you for that. However, actually, I would just like, before you call me that, to show the same data layout again, but with a slightly different visualization that emphasizes different thing. And here what I want to show you is assuming the first SIMD vector of this data is aligned, then what do all the other aligned SIMD vectors look like? And what you can see here is that if I take this SIMD vector and I do the equivalent of the scalar computation that we had initially, but with SIMD vectors, so I take it and I do a weighted sum of this SIMD vector, 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 and so on, I get the equivalent of the 3 scalar computations that would have been done using the same pattern. Now that may start to look interesting. How can we finish making the computation perfectly regular? Well, first, I will use the zero padding technique to show the alternate way to handle edge elements in stencil computations with zero boundary conditions. However, I am not able to do the same thing when it comes to the top and bottom elements. Why is that? Well, you see, if you look at the 1, 1 element in the original table, its top neighbor is indeed 0 and its left neighbor is indeed 0. However, this one, its top neighbor is this element, and this one, its bottom neighbor should be this element. And the way we are going to handle this is by creating on each iteration of the simulation a duplicated and shifted version of the bottom row and top row. So we take the top row, we shift it by 1 element to the left, and we put it here. And we take the bottom row, we shift it by 1 element to the right, and we put it here. And this we will do on every iteration of the simulation, but it will not be as costly as you may imagine, because we are only doing this for 1 line of the simulation domain and not for every line. So we have this a bit data shuffling, ugly thing going on, but for a sufficiently large simulation domain, unlike my schematics, the overhead of this particular computation will be negligible compared to the overhead of computing all the middle elements using SIMD. Sorry. So then I go into how the code needs to change to implement these data layouts. So now I need, in addition to my scalar data type, to have a vector data type, which represents a vector of scalar of some SIMD width. This is just a convenience alias for later. And then I need to make my storage generic over the SIMD width. So the intent here is that now, instead of having an array of scalars, I have an array of SIMD vectors, which will do 2 things. First, it will simplify my ND array iteration patterns. And second, it will ensure that the storage is suitably aligned for SIMD vectors. Because now this struct is generic, the implementation of its methods needs to be generic as well. By the way, this ugly thing is an implementation detail of std SIMD that is not necessarily final, but by the way, that's a way to say that not every integer here is a valid SIMD vector width. And then we will need to adjust our constructor so that it generates SIMD vectors with the appropriate pattern, which is done by detecting center elements in order to handle them differently, by translating the coordinates of SIMD vectors elements into the matching scalar coordinates, and then deducing the scalar pattern that we had in our initial code and translating that automatically to SIMD. We will also need, so the 0 part is easy, I will not get into it. We will need from now on to discriminate between 2 different shapes when we talk about the shape of our data. One is the SIMD shape, which is the number of SIMD vectors that we have in our simulation domain over rows and columns. And another is the scalar shape, which is the shape of the simulation domain as the user sees it, like how many, let's say, useful rows of data we have, how many useful columns we have. And here we want to count every scalar column, not full SIMD vectors of data. Finally, we need to implement the part where we update the top and bottom rows of the array on each simulation iteration. This is a bit ugly, partly because it has to be ugly and partly because that's due to some current Rust limitations. But ultimately we get there. Our double buffer becomes generic because the concentration type is generic over the size of SIMD vectors. However, at this point, we need to think, how many types we want to make generic in this way, right? It's good that we have some optimized SIMD data layout during our update loop, but we don't want, for example, the HDA5 code to worry about how data is laid out in memory. We wanted to think that we are just manipulating scalar data in the usual layout. And the way we are going to do this is that inside of a double buffer type, we are going to add storage for a scalar array of the proper size of the scalar dimension of our simulation domain. And then whenever the user requests the current concentration, we are not going to return a reference to the actual SIMD concentration arrays anymore. Instead, we are going to translate our SIMD data into scalar data and return a reference to our internal scalar data. And this is done using an operation that's morally equivalent to matrix transposition in linear algebra. So the idea is that if you have, let's still imagine that we have SIMD vectors of 3 elements, even if that's not realistic on a hardware level. If you have these 3 vectors, there are efficient sequences of instruction at the hardware level that allow you to take the first element of every vector, the second element of every vector, and the third element of every vector, and produces the resulting vectors of green, purple, and blue elements. And once we have that, then we can easily use these instructions to reproduce the original data layout from the optimized layout. Basically, we will take these SIMD vectors and turn them back into that scalar data. Now, the problem here is that here we reach the limits of what the STD SIMD abstraction layer in Rust can do. The sequence to do this is the optimal sequence to do this is extremely hardware specific and is beyond the current vocabulary of STD SIMD. So the way I have opted to handle it is to say, okay, well, these transposes anyway, even when implemented optimally, will be expensive. We do not want to perform them too often, much like we do not want to perform HDA5 IO too often anyway, because otherwise we will be bottlenecked by IO rather than CPU. And for this reason, I decided that I would just make this auto-vectorized. You can study the code later on to see how that's done. And it's probably not optimal, but for my purpose, it's fast enough. I have profiled it, and I know that for typical configurations that we have studied in the school, we are not limited by the performance of this function. Finally, once all of this has been done, I can produce my SIMD optimized computation kernel. And here you will notice that it looks exactly like our regular computation kernel from the previous chapter. And that's good. In fact, it's even simpler. We do not have this whole issue of loading a vector of SIMD from memory, storing back to memory with alignment or whatever. We just iterate over SIMD vectors from ND array using our usual pattern, the same one that we used in the scalar code, and it just works. And that's what we aimed for. We have a few more things to update to finish. We need to make sure that our simulation runner is aware of our SIMD data layout, because now it needs to be, unfortunately. And then in the HDA5 output method, we need to handle the fact that our HDA5 writer does not have access to the full concentration dataset. Because I have not mentioned it, but earlier we have simplified our vector to scalar translation to only produce a scalar array matching the concentration of the V species, since that's the only species we are interested in. So that we are changing a bit the interface of the HDA5 writer here, but not in a way that massively affects semantics. Okay, that was a lot. Hopefully it was not too confusing. Let me look a bit at your questions now. Greg asks, can we wrap around the simulation frame and take values from the other side instead? Yes, that's called the periodic boundaries condition. This we could do using index computations that would do modulo basically by the size of the simulation domain, so that we index from the other side of the array instead. Needless to say, integral modulo can be a bit expensive, so these kind of boundary conditions can be a bit trickier to implement efficiently in the naive pattern that we had initially. But in any case, as I have hopefully convinced you, for performance simulation, you will want usually to handle the center of the simulation domain differently than the edges. And then whether you use zero boundary condition or periodic boundary condition does not become something that affects the performance of the final simulation significantly.
Gotcha, thanks.
So Fatih asks, what we're doing here is basically a discrete convolution. Is there no way to make convolution with ND array? Well, that's what we did ourselves. Now, is there a built-in convolve function in ND array? This I'm not sure, but I mean, we could probably take the kind of code that we have studied in this course, extract it in a dedicated library, and we would be done. However, as I hope I have convinced you in later parts of my explanation, optimizing discrete convolution to the point where it performs optimally is quite a bit of a more involved process. You need to use a very different and a bit exotic data layout in order to get optimal performance out of typical SIMD hardware. And there, maybe that starts getting outside of the scope of what ND Array are trying to do here with their multidimensional array containers. So Marcel asks, I'm a bit confused as to why the updated code is not calculating things correctly. I assume this is about the part where we would regularize the computation by extracting the center part. If we initialize the border of the matrix to 0, this approach would never update the border and everything would work correctly. So actually no, but I need to get back to the code to show why. Let me share my window again. So once it will be done being slow. Yes. So why this loop doesn't work is that if you think about it from an iteration pattern point of view, and you say, okay, I have this array and I want to iterate over its elements in a sequence. Then it will first produce, maybe I will need a text editor for this actually. So let me change how I shared my screen to share the entire screen. So what I will do from the point of view of iterating over out is I will first extract element 0, 0, then element 0, 1, then element 0, 2, and so on. And So that's what I will get for iteration over output elements. For input elements, I will get the window that starts at 0, 0 and goes to 3, 3. Let's note it like this to be consistent within the array. And then I get the window that starts from 1, goes to 4. No, sorry, that's the first dimension. I stay at 0, 3 on the first coordinate, then I do 1, 4, and same here. So the point is, this window is actually appropriate for the output element at position 1, 1, not for the output element at position 0, 0. And that's why we need to adjust the loop so that we are iterating over center elements of the output arrays, as done next. Now, perhaps your question then, your sound is not very clear. I don't know if you can do anything to improve it.
Like this.
It's a bit better.
Can you hear me like this?
Yeah, that's better.
Okay, sorry. Yeah, so it was about the version with center actually.
So this one. So this
So
one,
because in the end for the exercise is said that you then have to do
options.
still treat
Yes.
the borders differently, and I didn't quite get why, because I thought with this approach the borders would never be updated, so they stay at 0, so all is good.
So maybe I confuse you a bit by trying to explain that there are two different ways to do this. So we can handle this edge problem in two different ways. Either we make the data more irregular by adding the strips of zeros around the edges. And in that case, this loop is the correct loop. But we need to be careful when we do SDA5 output, for example. Or we need to make the computation more complex by having one part of our computation handling the middle of the output, and another part of the computation handling the edges. But we need to do one or the other, otherwise the elements on the edge will not be computed correctly. I don't know if that makes sense.
Yeah, we don't want to compute the elements on the edges, right? They should stay at 0.
Sorry, the sound was not super clear again, but can you repeat that more slowly, perhaps?
Sorry, yeah. So we don't want to update the elements on the edges, right? They should stay at 0.
So that's one way to solve it. It's again, you can add zeros on the edges of your data. That's one option.
Yeah, right.
And the other option is you keep your data as it is, but you need to handle the edge elements specially. Is that
okay? Yeah, thanks.
Perfect. How does the updated data layout, data shuffling affect CPU caching? How does the updated data layout, data shuffling affect data caching? How does the shuffling will be, generally speaking, SIMD instruction sets are only good for processing very long sequences of aligned SIMD vectors. For everything else, you will be in a constant struggle as a programmer to manage to get performance that's even equal to that of your scalar versions. So the quick answer, and I could get into the more detailed answer, but it might take a bit too much time for the others. The quick answer is that the shuffling transposition will, in any case, be quite costly. To benefit from our optimized SIMD layout, we need this to happen rarely. Otherwise, it's not worth it. it will not just affect CPU caching, even if CPU caches will be affected because we are doing scattered memory accesses, and this can confuse the L2 cache prefetcher. But even at the SIMD level, all those shuffles will not perform very well on typical CPUs. The CPUs typically have a lot less compute power for shuffling data across vectors than they have for performing arithmetic. I hope, yeah, okay, perfect. Matthew says that in advanced SIMD, the data transposition required for I/O could be done by HDF5 itself with the right data space definitions. I don't know, I've never tried it. It would be an interesting HDF5 exercise. Just so you know, I actually learned about the required HDF5 features to do this after I wrote this course. But now, yeah, I'm a bit curious. Maybe I will try it someday. The quick answer is I don't know. I need to think about it a bit and draw lots of diagrams. Mhm. Yeah, there was also some discussion in the chat about someone getting the simulation even slower than it's supposed to be by accidentally forgetting to use the release mode of builds, which is the equivalent of running your code with O0 optimization in C, C++, and Fortran. You don't want to do that. I think that's it. So maybe I will let you work on this a bit more, and then I will cover some additional optimizations that we can apply to this computation. By the way, perhaps now is the right time to mention this. So I actually have implemented solutions to the exercises of all the Gray Scott chapters. And that's I prioritized this at the time because these chapters, as you may have seen, are meant to follow each other, right? Each chapter assumes that you've done the exercise for the previous chapter. So the way it works is that if you go to the repository that I am going to paste in the chat, that Git repository has a branch called solution. And if you look at the commits of that branch, each commit is the solution to one chapter from the Gray Scott part of the course. Now, unfortunately, the numbers of the chapters have changed since the time I have written these solutions. So you will need to add 2 to the chapter numbers. So chapter 12 becomes chapter 14 in the new version of the course, chapter 13 becomes 15, and so on. Hope that's not too confusing. But yeah, basically from each commit, you can see which optimization process I went through while writing this course. For some chapters, I give extra examples about what's going on. And then by checking out this commit and using that as your code, or just studying the diff and applying it to your code, you can get to the expected solutions for each chapter. So I also have one question from Greg about the fact that I regularly mention running a profiler, and it's not clear what the difference is with respect to running a benchmark. So maybe if it helps if first of all I clarify why we have micro benchmarks in addition to the main simulation binary. The intent here is to have an executable which only runs the CPU computation part of the simulation without running all the other things that the real simulation does, like opening HDF5 file, writing data, maybe compressing if you're using compression, and so on. And having these micro benchmarks allows you to get a cleaner CPU profile in the next step, which is to apply a CPU profile to your micro benchmark. This course is unfortunately a bit too short to get into the details of how CPU profilers are used, but hopefully you will be able to find some resources on that. But essentially, the idea would be then to apply, once you found some CPU profiler that you like, to apply it to the cargo bench command that you used for running a benchmark. It will be helpful to this end to know that when you are using cargo bench, you can actually select which benchmark you are running and run only that benchmark. That's done by typing a regular expression at the end of your cargo bench command, which selects which benchmark you are interested in. Like, for example, oops, sorry. this cargo bench command would only run those benchmarks whose name starts with float. And that's a way when you have many benchmarks to only pick up those that matter to you because you only change a part of the code that pertain to those benchmarks. That's the first thing you can do to make cargo bench easier to use with profilers. The second thing you can do is to use one command line argument that Criterion accepts, which from memory is called profile time. I need to check this. And when you do that, what will happen is that normally, Criterion, when it runs a micro benchmark, it does many measurements, it does some statistics in order to tell you what is the average value of the measurement, what is the minimum, maximum, 95% error bar, which measurements are outlier, and so on. If you do a CPU profile, you will not only get CPU profile of your code, but also of the Criterion statistics code. By using this command line flag, profile time, what you get instead is that Criterion will only run your code in a loop for 10 seconds without doing anything with the benchmark results. It will not even measure them actually. And as a result, you will be able to run your micro benchmark in such a way that your profiler will only see your code and produce a very clean profile that's very easy to interpret. I guess there would be a third part of your question of how we know from the profiler output that the bottleneck is index calculation.
Actually, sorry, maybe you got me wrong. I know what a profiler is, but in this section regularization, you mentioned about that it seems like we should already know that this part will take a lot of time. So is it already contained in the code? Are these micro benchmarks? I don't think so, and that's what I'm asking. Whether we should put these micro benchmarks here around these code parts to actually find out which part takes the most time, right?
You shouldn't need to. The idea is that if you have enough experience with using profilers that work at the assembly level, like perf, then by studying the output of perf on the full computation, you can easily find that specific functions are the bottleneck. And by looking at the name of these functions or their assembly to see what they do, you will figure out that actually these are functions involved in the computation of indices and scalar windows. Is that clear?
Yes, because I used I'm not an expert, but I used the profilers a couple of times in my lab. But here I don't see a profiler output in the benchmark output, and I don't see specific functions calls and their how often they are called, how much time the CPU spends in each of these functions. So I only see the benchmark output in the command line, and I don't see like any mention of the functions that I would expect to see in the profiler output.
Yeah, because that was not a profiling course and I didn't want to spend too much time. So here, I'm just giving you the answer,
Okay,
assuming
so the answer is we without running the profiler really, or we couldn't know that in section
it would
5.
be harder to tell that because the
Okay.
indexing computations are mixed with all the ALU calculations. So it would be hard by just putting timing code in your code, for example, to tell that the indexing is the bottleneck, not the ALU code.
Okay, because I thought I missed something, and now okay, I understand. Thanks.
No, it's just a shortcut that I took to make this course a bit shorter. So Matthew had a hard time finding the solutions in the repository. So here the idea is maybe it will be easier if I show my screen. So the code for this training, and I'm not talking just about the exercises code that you have been using so far, but everything like the code that's used to generate the website that you're seeing is inside of a repository whose URL I have typed in inside of the chat. That Git repository has two branches. One is the main branch, which is the version that dictates which exercise source code you download, which version of the website is online, and so on. And there is a second branch, which is called solution. Compared to the main branch, the solution branch has more commits. It's actually based on top of the main branch. And yeah, that's a bit of a Git trickery, but I can tell you that the part that's specific to the solution branch starts here. And you can see that starting from the main branch, you get new commits where each commit implements the solution to one chapter. And that means that by going through the Git history with Git checkout, for example, or graphical Git client, if you're more comfortable with that, then you can get a version of the exercises source code where one particular problem has been solved. Like this commit is a version where I have solved the problem at the end of what was at the time chapter 12. I need to update the numbers. This one is what happened after that when I also solved chapter 13, and so on. Does that clarify the thing, maybe?
Well, yes, but I was looking for the solution of chapter.
So I don't
the new
have
chapter
one
12
directory with each solution because the solutions built on top of each other.
yes.
So
No,
instead,
but that's fine. But so it looks like all solutions are for the Grayscott code, right?
Indeed, I do not yet have solutions for the first chapters. This has been asked for before, and I'll try to make it for the next edition of the school.
Okay, yeah, because I can't go through the chapter of parallelism, so I don't get speed up, and I cannot mix it with SIMD. So I was really interested by the solution on that. But okay, anyway, thanks.
But we will have some parallelism at the end of the Grayscott chapter, so maybe we can get back to how it's done then and see what you don't understand. I don't know. Let's hope that's a yes. All right, so unfortunately time is moving and we only have 30 minutes together left. I would like to get together with you on some of the chapters because they can contain a bit of tricky concepts. So I would like to move forward a bit and do some explanations of the next ones as well. So let's get back when we started. So if you got the time to go through the chapters and do the exercises as intended, one thing you may have figured out is that we have spent a lot of time implementing optimizations that should make our vectorization faster. But if you do measure the performance, you will find that actually the computation, when you apply these optimizations, actually becomes slower. So that's a bit of a paradox. So let's see if we can explain that. And to that, I will actually need to answer. I will actually be, well, by answering this question, I will actually also be able to answer one of your questions from, I don't remember if it was Monday or Tuesday, of is there any limit to zero-cost abstractions in C and C++? And at the time I told you, yes, there are many limits. One of them is that they are extremely reliant on one particular compiler optimization, which is called inline expansion, or sometimes shortened to inlining. The idea of inline expansion is that sometimes compilers, when they see a function call, may decide to not actually generate the corresponding function and call it at runtime, but instead take the implementation of that function and copy and paste it inside of the caller code. This will have two effects. First of all, you avoid the overhead of function call, which is small but can still be a problem if you're calling a very small function in a very tight loop. And second, another problem, another thing that inlining will do is to enable other optimizations. The problem is that as developers, we do not have that much control over this compiler optimization. Compilers basically decide whether it's worthwhile to inline a function or not based on complicated heuristics that make assumptions about how your code will behave at runtime and that try to balance a complicated trade-off between, on one hand, improving your runtime performance. On the other hand, you don't want to overflow the CPU's instruction cache. You don't want the output program to be too big. You don't want compilation to take forever, because anytime you inline, you basically create many copies of a function in the program code, so the program code goes bigger. And sometimes the heuristics end up picking a trade-off which is highly unfavorable for the runtime performance of your own code. What tools do you have when this happens? In Rust, many times you can solve these problems by using a magical compiler directive called inline. You annotate a function that you want to be inline with this annotation, and then the compiler has a higher chance to inline this function, because what this does at the compiler level is to modify the heuristics of the compiler backend so that inlining the function seems a lot more worthwhile than before. One thing that may not be obvious here is that this will affect every use of the affected function. You cannot just choose to inline a function at one position of the program. You can only choose to inline it everywhere. Anyway, many times that's a bit of a sledgehammer approach, but it will often be enough to restore inlining where you want it, where you want to have it, and bring back the runtime performance that you would expect with a properly inlined abstraction. Sadly, inline only modifies the compiler cost model by making inlining seems more worthwhile, And if the compiler is strongly convinced that even with the hint, the function probably shouldn't be inline, it still won't inline it. And that's where inline always comes to play. It's a much stronger hint. It tells the compiler, okay, no, let's be real. You should inline this function always everywhere, even in debug builds. I don't want to ever see a call to this function unless it's simply impossible to do without calling this function. One example of a situation where this is impossible is recursion. This is all fine and good. The problem is we are, in the 21st century, and we do not anymore have programs where all the code has been written by ourselves. Many times we are calling functions from libraries that are written and maintained by other people. And in that case, it means that we cannot easily control how the functions from those libraries will be inline into our code. We need to submit patches to upstream, hope that they will accept the patch. They may not, because they may think that inlining the function is usually not worthwhile, and we are just in some kind of edge case where it is worthwhile. And yeah, that's a bit of a pain when you end up in this situation. I wish to live in a future where compiler provides us with more options here, but as of today, there are essentially 3 options. Option 1 is what I just said. You get in touch with the developers of the library, you try to get them to add inline directives. You wait for the next release, or you use a local patch to get the inlining you want while you wait for upstream to get things moving. It should be noted that not every library is easy to patch locally that way. For example, you don't want to maintain local patches to the standard library. Second option is to tweak the code on the caller side in the hope that you will get it in a shape where you get better inlining. That's very time consuming and highly reliant on some experience. Essentially, you need to have a mental model in your mind of how the compiler optimizer works and know which factors influence its inlining decision and try to not stress those particular factors too much. And finally, option 3 is to just say, fuck it. You take the function that failed to inline, you copy paste it inside of your code, you modify it how much you want, and you put as many inline directives on it as you want until you get the performance you want. But then you need to basically maintain a partial fork of some library, which is not nice. Let's start by the easy things. How do we know where inlining issues happen? The easy way usually is to look at the output of, if you're using perf report without call graphs. And here you will see that there are some functions that have huge overhead. And if you look into how these functions are implemented, and you know a bit about what kind of optimization inlining enables, you will see that you really want these particular functions to be inlined. Here, these 2 functions should be inline for different reasons. The second one is easier to understand. So it's the iterator that results from, when we compute your Laplacian, you need to jointly iterate over windows of the input data and over the stencil weights. And that's actually one part of this iterator pipeline. And the problem is you really don't want that iterator not to be inline, because if it's not inline, then you will not get some powerful loop optimization to the resulting Laplacian loop, including loop unrolling, and that will cost quite a bit of performance. The other one is a bit trickier to understand why it should be inline. You need to know how the multiversion library that we are using for runtime Cindy detection works. but sufficient to say that if this is not inlined, then it will defeat multiversion's attempts to generate optimized copies of our code for different SIMD instruction sets. Instead, the compiler will generate just one unoptimized copy and call it from all the code paths for different SIMD instruction sets, which is very much not what we want. The first issue with the Laplacian iterator is actually easy to solve when you know the trick. It's just an ugly trick. Basically, the problem is that here, when we are doing into iter on a 3x3 ND array window over our input data, we are asking ND array to translate a two-dimensional array object into a one-dimensional array, one-dimensional iterator. And the code that gets generated is just complicated enough that the inliner thinks, okay, I'm not inlining that, that's weird. The funny stuff, however, is that if instead you do iteration over rows of your input windows, and then you modify the iterator to take those rows and turn them into a different iterator, which is an iterator over element, and you use some combinator called flatmap, which allows you to flatten the inner iterator so that in the end you get one single iterator that goes column by column, then row by row. You will get the same effect as this, but because each iterator combinator is individually simpler, you will not go above the compiler's inlining threshold, and therefore the compiler will accept to inline individual things and eventually inline the entire iterator. So that's what I meant earlier when I say that with experience and lots of trial and error, sometimes you can tweak the caller side code to get in the shape where the inliner is happier. As you can see, it's a bit of a black art and not something that feels very nice, right? The second issue is more difficult. If you look at the function that fails to be inlined, which is the zip producer from ND array that we use in our loop over joint loop over windows and output elements, you will see that it's actually quite complicated because ND array has to manage arrays of arbitrary dimensionality, and that requires relatively sophisticated computations, complicated generic code, and so on, that eventually should be optimized into something simple and fast, but in the beginning is a large amount of code. And the problem is the inliner pass of the optimizer is run too early in the compiler cycle, then the compiler will say, oh, look, that zipping is too big, I'm not doing that. So what do I do then? Well, this is the point where I do the third option I mentioned earlier, give up and just rewrite the code myself. And because iterators, in order to avoid bound checking, involve unsafe code, this means that it's a good occasion to introduce to unsafe code. So as a reminder, one key idea of Rust is that most of the code that you write should be proven at compile time to be type safe, memory safe, and thread safe. If it cannot be proven at compile time, it should at least be proven at runtime via runtime checks. To be concise, we call code that has all these nice properties safe code. The problem is not all code is amenable to this kind of proof. There are some operations whose correctness cannot be proven at compile time. Like, for example, if you call into a third-party library that is implemented in C or C++, the code that is written inside of these languages is not proven to be safe by the above definition at compile time. It does not document its runtime safety invariants in any formal languages. Indeed, usually it does not document them at all. So there is no way for the Rust compiler to prove at compile time that calling a C or C++ function is safe. It cannot even prove it at runtime. It just doesn't know what conditions must be met in order to achieve type safety, memory safety, and thread safety when calling this function. However, we do want as programmers to be able to call into C and C++ function. And that means that we need to have some kind of manual proof mechanism that allows us to manually assert that actually, if these functions are called in particular circumstances, then we should keep all the safety properties we care about. Sometimes we can use runtime checks. But as the name suggests, they have a runtime performance cost. And sometimes the compiler optimizer is able to remove the performance cost, and sometimes it's not. And unfortunately, often it's not. So this means that when we get to the situation where the runtime checks start happening too often and costing a non-negligible percentage of our CPU time, we need to take the matters into our own hands and use unchecked code that can exhibit undefined behavior if used incorrectly in order to eliminate the runtime checks in the places where there are problems. All of this in Rust is handled using the unsafe inner dialect of the language. The use of this dialect is guarded by use of the unsafe keyword. For our purpose as numerical scientists, the main use of the unsafe keyword that we will run into is eliding runtime checks and replacing them with code that may exhibit undefined behavior if called incorrectly. And the way it works in Rust is that we will have we will have two new entities. We will have unsafe functions. These are functions that, if called with the wrong parameters, result in undefined behavior. And these functions must be, in Rust, documented to spell out what are the circumstances in which calling them results in undefined behavior. Not documenting is not an option. And we have unsafe blocks, which are regions of code in which we are allowed to call unsafe function. And here the idea is that the best practice, at least, is to document this unsafe block to say why you think that in the particular circumstances where you sit, it's safe to call these unsafe functions. Like, I know that the indices are in bound because I computed them like that, and so on. A bit of warning, sometimes when people from C, C++, and Fortran discover unsafe code, they start using it everywhere. That's not idiomatic behavior in Rust. If you want your code to be well accepted by the Rust community, you should only use unsafe in situations where you are pretty sure that there is no safe way to resolve your problem. Knowing that even some people consider that it's better to tweak a bit the shape of your code sometimes to get the compiler to optimize the code rather than to use unsafe, which is dangerous and can result in undefined behavior. And other things that you need to keep in mind when you use unsafe is that if you did not mark a function as unsafe, it must be safe for all combinations of inputs. If it is marked as unsafe, again, you must document in which circumstances using it is safe. So with this introduction, let me introduce you to my homemade implementation of the ND-array iterator that I need, which uses pointer arithmetic and all sorts of cursed and forbidden stuff in order to produce the right output references and input windows that I need. And all that just to slap that little inline directive on top to make sure that then the iterator will be properly inlined, and thus I will get the optimizations that I need. So I hope that answers the question of what can go wrong with zero-cost abstraction. After that, we can resume our usual code optimization schedule that you studied in the first chapters on a simpler computation. So first of all, you may have seen that our code is full of sequences of multiplications and additions. And you may know that on most CPUs, fuse multiply add is it costs the same resources as doing a single multiplication or a single addition. So effectively, it gives you 2 floating point operations for the price of one. So you may want to just, take this code, find every sequence of multiplication and addition or subtraction, replace that with multiply add, and you may expect that your code gets 2 times faster. What you will find out, however, is that unfortunately it will instead become 7 times slower. And now you may wonder why that is. Well, I mean, how much slower it gets depends on the problem size. We can get into why later, but it gets much slower. So the problem here is that when we say that a certain operation is fast or slow in hardware, usually what we are talking about is throughput. We are talking about assuming the CPU has an infinite amount of fuse multiply add operations to execute. How many of these operations would it be able to execute each clock cycle in the steady state? And the problem is there are plenty of strings attached when you look into the details. CPU instructions actually have a latency. You need to wait for the results to come out. You can only exploit your full throughput if you have sufficient amount of independent instructions to execute. To make matters worse, fuse multiply add have a slightly higher latency than additions. So if you used to have a dependency chain linked to addition, that dependency chain in the presence of fuse multiply add is even more costly. And finally, multiplication and addition in SIMD are very flexible operations because on you can have at the hardware level ternary assembly instructions, which means that you can fully decide which registers you get data from and which data register you emit the result to. This is not the case for FMA because FMA have 3 inputs, not 2, and this means that the combinatorials are not so nice. You would need to have a huge amount of FMA instructions in order to cover all possible combinations of multiplication, addition or subtraction, negation, and input and output registers. And as a result, CPUs only implement specific patterns. If you go outside of these patterns, you will get bad code. All that to say that overall, FMA in hardware has been designed to get a high score at LinPack. If your code looks like LinPack, it will perform well. If it's very different from LinPack, it will perform very badly. Knowing this, we may want to tune down our FMA ambitions a bit and only apply them inside of the Laplacian loop, where they seem more useful, perhaps, and where they are least likely to be part of a dependency chain that FMA would worsen. If you do that, you will find that no, your code is not much slower than the original code, but it's still not faster. And to get it to be faster, you will need to break the dependency chain. You will need to find how to make this accumulation loop exhibit many different parallel FMA operations so that we can keep our CPU busy when it's waiting for results. And here, unfortunately, you cannot use the nice library that I wrote because it is missing one important optimization to get it right. So you will need to write the code the old way, as you would do in Fortran. And it looks like this. We can start with two-way instruction level parallelism, where we are computing 2 values of u and v in parallel, see what that gives. And that gives us quite a nice speed up. We get to 8 times faster. You see that this is more than what we expect from FMA because actually even the original code was starved for instruction level parallelism. You can try to get it with even more instruction level parallelism And on my Intel CPU, it does not change much. And actually, no, I know why. It's because of how they handle subnormal numbers. But at the time I wrote this, I didn't. And but I can tell you that this is still beneficial on my AMD CPUs at home, which do not have such a penalty for subnormal arithmetic. They still get a 10% speed up when you increase the instruction level parallelism even further. And finally, if you try to get the maximal amount of instruction level parallelism at the expense of losing FMA, then it's slower, and that's expected. You're not using FMA anymore. We only have 5 minutes left. So unfortunately, it looks like I will not have the time to get back to the question of parallelism. Just to give you, unless Mathieu, you want to stay a bit more after the end of the time slot. Anyway, just to give you a picture of what the last chapters were about. So the next chapter shows how we implement cache blocking in Rust. Unfortunately, there's something weird about this chapter where the cache blocking optimization ends up not benefiting performance, and I have not yet found the time to fully investigate it. So I keep it around because I suspect that this is just a case of CPUs becoming clever enough to do the cache blocking for you in simple loops, and in more complex loops they would not be able to. If that's the case, then it's still good to know what the pattern looks like, and it's also good to know if you need to target less sophisticated CPUs like ARM CPUs, for example. And then I go on to parallelism, and the way I handle parallelism basically is by adding another layer of loop blocking on top of cache blocking, which is about creating independent blocks of instructions for the benefit of the parallelization. I hope you enjoyed this course. I will now answer your last few questions, and then it will unfortunately be time to close this session. Before you go, please fill out the poll that I made. So this is the first time I run this course independently rather than as part of the Grace Code School. And I suspect that some chapters are a bit too quick in this context. There are some concepts I should probably spend more time explaining and so on. So the intent of this survey is to gather which modifications would be needed to make this course work better for you in a standalone format. And so, yeah, please fill it. It will help me do the next revisions better. Meanwhile, I will look at my Q&A, and so far there is only one question. John is asking, does inline always make every calling function produce code for every data type used before morphization? Actually, yeah, as Eric points out, you always get that with standard generics. Generics in Rust work like template in C++, where the code of the generic function is copied and pasted for each combination of type and value parameters. Sometimes this can be a good thing, other time it can lead to major code bloat and cause all kinds of problems. Indeed, generics are a good recipe to create lots of code, and when you combine generics with inlining, it can sometimes happen that you create even more code from what looks like an innocent function declaration. I actually have an instance in my ISWLock binding where a single generic function gets translated to no less than 100 functions in the final binary. And obviously you can guess that I tweaked the code of this function so that the overhead of compiling it is minimal. All that being said, the combinatorial explosion is not as big as you suggest, because often generic functions are not called with specific combinations of inputs from many different places in the code. Usually they get called with one combination of parameters from one place in the code, another combination of parameters from another place in the code. And therefore, usually the overhead tends to be linear rather than quadratic in the number of instantiations. Can you advise me a good grade for automatic differentiation? Unfortunately not. I have not studied this topic so far. I know that there's some ongoing work to integrate automatic differentiation directly into the Rust compiler. It has started this summer. It might be a while before it's fully released in a stable compiler version. Meanwhile, yeah, I have not yet needed automatic differentiation, so I cannot tell you which of the available external libraries do it best. If you do not see the poll, you might be able to get to it by using the More button at the bottom of your Zoom window. And then from this More button, you get a menu. And in this menu, you should have some kind of poll quiz button. If you click it, it will open a new window. And in that window, you can answer the poll about how easy or hard each section is. Would it be too penalizing for performance to rewrite the Grace code simulation in a more traditional syntax like V equal V1 plus A times V2 instead of iterator chaining? I'm not 100% sure what you mean by traditional syntax in this case. Maybe you mean a loop over indices? If so,
no, I mean to write the code like this by manipulating vectors and redefining, for example, operators like add to how can I say it, to put iterators behind the stage, which are not really visible.
oh yes, you can totally do that. We have a number of linear algebra libraries that provide you with linear algebra vector matrix types that can behave that way. However, I don't think you can easily use a linear algebra library to implement a stencil computation along the lines of what we are doing here.
But for doing stencil operation, it's just basically the same operation that I have put in question, which you update a vector with multiplying by another vector. By vector, I mean a row of the array, something like this.
Yeah, that could actually work. I guess my main worry when it comes to performance is that I think if you expressed it in that way, you would have to materialize the intermediary vectors, which would probably cause a memory allocation. And then I really hope the compiler would manage to elide this memory allocation.
Could not be just the slices.
The inputs, the slices are fine. The question is, can you express the output operations using just slice operations that operate in place? This I'm not sure, maybe.
Okay, thanks.
Adrien,
Mm-hmm.
before the end, can I suggest something? Because
Yes, of course.
because you are one of the teacher of the Grace Code School, perhaps now I think all the attendees are aware about the Grace Code reaction and of course your amazing training. Perhaps you can introduce the Grace Code School and invite them to come with us next year, perhaps. I
Indeed.
think you are the best guy who can introduce that. Thank you, Adrien.
So again, as like Karim pointed out, this course is actually originally just one course module as part of a larger school that we've been organizing with colleagues all over France, which teaches you how to perform computations on CPUs and GPUs using various technologies. We cover C++, Fortran. For the GPU side, Rust. We want to cover Julia next year. On the GPU side, we cover CUDA, SQL, OpenACC, I believe, maybe OpenMP, I'm not sure, but for the Fortran side. We used to cover Vulkan in the previous edition, but I will be just doing a talk next time rather than a full course, because as you can see, my courses tend to be a bit difficult for the time budget we have. In this particular case, we decided that maybe we could just use that time budget more efficiently. So that's a school that's of a relatively long length. We are talking about 2 weeks of work. 1 week where we cover CPU work, when we cover how to write efficient code for CPU, 1 week where we cover how to write efficient code for GPU. We used to do it in French so far, but next year we want to take it to the next level and rewrite everything to English. And actually some of the slides that you have seen during this course are some early translations that will serve as part of this next school. And because we want to take it all over Europe, and actually this year we already wanted to take it all over French-speaking countries, we have made it so that you are not forced to come join us at ANSI for the in-person training, even if that will be the best experience probably. You can also join us either from your home over Zoom or from HPC centers that we call satellites, where you will find machines like Devana in this training and people that can help you when you run into problems in the exercise and help you locally. If you are working at an HPC center, or you know of people who do, and you are interested in hosting such a satellite site, please get in touch with the organization team. You can send mails to Karim, Mari, or me, and then we will discuss how that's done. Actually, we have not even fully figured out the procedure yet, so there's plenty of time to tell us that you are interested. If you have any questions on that, we can talk about it more. What's the cost? We don't make people pay anything. It's free. However, if you come in person, we will not pay for your hotel room, for example. So you still need to pay for the travel and I think the dinners. But last time we managed to offer lunch to people. I'm not sure if we will manage this time. When is the training? It will be in early July. Let me cross-check the precise dates, but probably Karim knows them by heart.
It's the last week of June and the first week
last
of
week of
July.
June, first week of July.
Yeah,
Okay.
it's totally free. If you want to host the school, you can do it. We are not going to ask you about money. It's totally free, and we are really happy to make it in English with the other teacher, with Adrien, and of course to have a different satellite everywhere in Europe, but depend on if you want or not. Thank you very much, Adrien. It was
And
3 days
to repeat,
amazing.
since Greg did not believe it, yes, you can join online.
Yeah. In 24 with
Yeah,
all the
incredible. Thank you.
it's just to give you some input.
In 25.
In 24 we learn I think something like 500 people during 2 weeks. 500 different people during 2 weeks. Each days during the 2 weeks we have more than 200 people connected, so it was just amazing. And perhaps in 25 we are going um, to have perhaps 1,000 people, something like this. So it's going to be amazing, but we can do it.
We've done it before.
Yeah. And of course, if you want to come on the mountain in Annecy to talk with the teacher, to eat with the teacher, you are welcome. We have something like in 24, we have something like 20, 26 students. And in 25, we are going to open to 60 people in Annecy. So if you want to come, it's not a problem.
So, Greg, we are still in the middle of organizing the next edition. So we do not have a registration website up yet, but as Mary mentioned in the chat, as soon as we have, you will all be informed. We will all send you all an email. Where is it? So if you want to attend in person, it will be in Annecy in France. That's in the Alps, next to the Swiss border. If you want to, if you want to see the teachers in person, that would be there. If you want to still have an in-person event, but closer to where you live, then wait a bit until we know the full list of participating HPC centers, and then we'll be able to tell you which ones are closest to where you live. And finally, if you want to attend online, you can do it from everywhere.
And if you want to become a SID satellite, of course, just tell us and we can make it. In 24, we had something like 12 SID satellite in 4 countries. I think it was 9 in France, 1 in Belgium, 1 in Morocco, and 1 in Senegal. Something like this. So we are going to extend it, and all the country who want to become a SID satellite, of course, we are going to create it for free. So if you are interested, just send us a mail, and we are going to make it.
Thank you. I started thinking about visiting Annecy with my family at that time. I see it's near the lake, so it must be a beautiful scenery,
Oh
right?
yeah, it's
yes, it is.
and if you like hiking, also there are some really nice places to go in the weekend
Yeah,
in the mountains
also.
nearby.
But during the
The
2 day,
limiting factor would be the cost, maybe. Yeah.
yeah,
Yeah, with a larger family, especially. Yes, sorry, but I interrupted you.
no, it's okay, it's okay.
I didn't get that.
So no more question, no more comment.
Yeah, if there are no more questions and comments, that maybe we can just close this for now.
Yeah. Thank you very much, Adrien, for this 3 days. It was really amazing to have all these people with you to learn about Rust in CPU. So just to say thank you very much, Adrien. Also to say a special thanks to NCC Slovakia, who co-organized this training, of course. And we hope you enjoy it. Thank you for the reply to the survey, because we are going to perhaps it's going to help perhaps Adrien to improve. I don't know if we can improve it, but we are going to see. And
Of course we can.
yeah, and that's all for me. But just to say really a big thanks, Adrien, for your time. Thank you very much.
Thanks a lot for all the kind words.
Thank you so much, and bye. Maybe
Bye.
see you.
Hopefully.
Yeah.
So we are going to close this training. Thank you so much, and I hope to see you soon.
Thanks.
Bye bye.
Bye.